everybody, and thank you, Nathan, for your opening statement there. We're going to kick it over to the globe side. Dr. Tony, I'll ask you to go first. You have 6 minutes to present the case for the globe Earth, and thank you for so much for being here.
Well, thank you, and thank you for the kind welcome from my interlocutors, and thank you to T-Jump for agreeing to appear with me. Let me just start my share. Here we go. Can you see that?
Yep, we are coming through. I can see your
Okay,
presentation.
so we've got two models, and the key question as to which model works best is to compare those models versus observations. That's the key element of science. If one model fails to give predictions, then it loses by default. You don't get to just win a competition by saying, sure, I can do that. You have to actually do stuff. So let's look at the most basic navigational problem that you can face. You know where you are, point one, you know the latitude and longitude, you know where you want to go, point two, longitude, theta two. How far away is it, and what direction do I need to go in? Now, if the Earth is a flat and we accept that one angle of separation corresponds to approximately 69 miles or 111 kilometers, then this should be an easy solution on the flat Earth. We know the two sides of the triangle, and the angle between them. We can work out the third side and the angle psi. If you accept that geometry, then this is your flat Earth map. There's no other map that has those properties. The way we do it with a spheroidal calculation is exactly the same, except that it's a spherical triangle. We know two sides, we know the angle between them, we therefore solve for the third side and the angle psi, and these are the formula that give those. Now, this is a very long-standing problem that a lot of people have been faced with. When Bly and his 18 crew members were thrown off the Bounty, they had to navigate 7,000 kilometers to safety, and they had to do that without making landfall. The first time that they made landfall, they got attacked by islanders, and one of their crew was killed. So they had to work out how much water they had, how much food they had, could they make that journey without making landfall? And they were able to do it. Similarly, the Shackleton expedition to Antarctica, their ship, the Endurance, got trapped in the ice. Then it got destroyed in the ice. Then they camped on the ice until it melted. And then they took rowboats to Elephant Island. From Elephant Island, 5 of them had to navigate 1,500 kilometers, or almost 1,000 miles, to get from Elephant Island to South Georgia. And they made it. Had their navigation been off, they would not have. We have hundreds and thousands of intercontinental marine transports every day. We know what techniques they use, and we've been using them for hundreds of years. Here is a manual, a sailor's manual from the 17th century, written by Samuel Sturmey. And it's the problem it's discussing here is how to navigate from the mouth of the Amazon to the island of Lundy. We can show that they use spherical geometry to do that. The flat Earth is incapable of telling us how much fuel, food, and water we need. It's not capable of giving us those answers. You can't just say that your distance formula is the same as the spherical distance formula. That won't work. If you do that, then you have to agree that the distance from McMurdo Station to Mawson Station is 3,000 kilometers, not however much you need. Similarly, we use the same navigation techniques for aircraft, and we have done here, for instance, 5 intercontinental air journeys. What I've done is I've averaged the outbound and the inbound flight times, which are in red in that 4th column. I've multiplied that by the average cruising speed to give that 5th column, and I compare that to the spherical distance estimate in the next column. The final column is the flat Earth distance element, and you can see that the flat Earth distance elements are generally larger than the aircraft could travel in that time frame. For Sydney to Santiago, which is the shortest flight in terms of time taken, the flat Earth says that it's actually almost twice as long as it is in practice. Meanwhile, flat Earth tells us that the shortest of these flights is actually Seattle to Dubai, which is one of the longer flights by time taken. Again, Flat Earth fails to give us aircraft fuel requirements or food requirements. We can actually check physical objects. Here we have submarine cables, one submarine cable going from Sydney to Hillsborough. We can compare the cable length that we know versus the spherical distance formula and the flat Earth distance formula. We can see that the flat Earth distance formula is several thousand kilometers. Well, it's more than 1,000. It's about 1,000 kilometers too long. Even at 100% tension. We can have a look at the Perth to Muscat one. We can see that again, the flat Earth distance is just too long. There are hundreds of these. Similarly, we can look at railways. So here's a physical object. The railway between Kalgoorlie and Tukula, we can measure the track length. It's 1,280 kilometers. If we look at the spherical distance estimate, that's 1,240 kilometers. The flat Earth estimate is 3,000 kilometers. So we can show that the flat Earth does not get that right. Similarly, we can look at Jacksonville to Pensacola. We can see that the track separation is 593 kilometers. The spherical distance is 533. The flat Earth distance 643.
10 seconds.
We can now check the geometry. Flat Earth suggests that distance between longitudes should increase with distance south. It doesn't. We can show that here, but we can also go to Argentina and see that the track length in Argentina is even shorter than the Northern Hemisphere track length.
All right. I just ask you to stop the screen share, and thank you so much, Tony, for your introductory statement.